Welcome to Introduction to Abstract Machines. This is the first part of Chapter 3. My name is Theo Kim Heng and from Informatics. The main objective of this course is to find the ultimate definition of computation, computing, or algorithm. We have used these terminologies day in and day out without really understand the meaning. If computing is a science, we cannot afford to have no clear definition of this fundamental concept. Roughly, computation means step-by-step work by a machine for the purpose of solving a computational problem. Then, what do we mean by problem? What do we mean by machine? Let's look at the definition of problem first. A problem is a mapping from a set of instances to a set of answers. We have used programming language such as Java to write a function. And if you look at the function, it got input, it got output. And the specification of function is what are the input and what are the expected output. The specification of the function means the problem for the particular function to solve. For example, primarity problem is a very important and famous computational problem in computing. In this problem, the instances are integer, positive number, natural number, and the output are yes or no. For example, if the input are 23, 19, or 13, all these are prime number. So we say that the output is yes. It's a prime number. Otherwise, like 26, which is the proper factor, such as 2 and 13. So the expected output is no. You may say that this is a very simple problem. We know how to do so-called prime factorization in primary school already. But we are looking into huge number, a number that had, for example, 100 of digits. I give you a 100-digit number, and I tell you that this number is a product of two numbers. That means x equal to y times z. I give you x, 100 digit. It will be very time-consuming to find y and z. And this actually is the heart of so-called RSA, public key infrastructure. So, for this problem, the instants are natural number. The answer, according to specification, is the answer should be no if it can be factorized into two factors, proper factor. In other words, if you can find, if there exists a number p such that p doesn't belong to 1 and n. In other words, p is not 1, p is not equal to n, and p divide n perfectly. Okay. For example, if n equal to 26, then we can find a p which is 2 which is not equal to 1 and 23, and 2 divided by 23. 2 divide 23 perfectly. So in this case, it is not a prime number, the output should be no, otherwise it's yes. The primary problem belongs to a class of problem, we call it decision problem. Decision problem just asks for yes and no, true or false. Intuitively, on the surface, it seems that decision problems are much simpler than the other type of problem called construction problem. Construction problem asks for a solution, which can be a complex object. And decision problem just says yes or no. It seems to be easiest. For most situations, a general construction problem normally has a corresponding decision version, which is as difficult as the original construction problem. In other words, for a construction problem, most likely you can find a decision version. And if you can solve the decision version efficiently, then you can solve the construction version efficiently too. For example, let's look at the factorization problem, the construction version. So in this problem, the input is a natural number n. For example, n equal to 4141. And the expected output is the prime factorization of n. For example, n can be factorized to 11 times 13 times 29. So this is not a decision problem because this asks for the prime factorization, which is not yes or no, but all the factor of the input n. For this construction problem, let's look at the decision version. For the decision version, input is a pair, a natural number n, such as 4141, and another auxiliary threshold, k. For example, k equal to 10. Then the decision version asks for true or false. And the expected true if and only if there is a number d within the range 1 to k, such that the d is a proper divisor of n. So the question asks for whether there is a d in this range which is a divisor of n. The expected answer is yes or no. You can go to CN class, try to provide your solutions of the construction problem based on the decision version. In other words, you can go to CN and look for this challenge. So in this challenge, you supposed to have an efficient algorithm called factorization decision version that take a number n and a threshold k, and this function already available, and it will say true if there is a number in 1 and k such that d is a divisor of n. Given this algorithm, you are asked to design an efficient algorithm that can solve the construction version of the factorization problem. Share your design in CN discussion forum, and this will worth 5 marks for your participation. If we agree that decision problem and construction problem are equally difficult to solve, in other words, if you can solve the decision version, you can solve the construction version for most problem that we face. So, in theoretical study, we can actually just concentrate on decision problem. In other words, when we say problem, we actually refer to decision problem only. So the next question is how to specify a decision problem. Let's consider a problem corresponding to a mapping F. So in this problem, these are all the possible instances. Some of the instances, we map it to yes. The other instances, we map it to no. So, if we know what are the yes instances, the problem will be well defined. In other words, if we can find the set of yes instance, meaning the set of S such the mapping map S to yes. If we know this particular set, then the problem is well defined. So, in other words, a problem is a set of instances corresponding to the answer yes. Let me summarize. Problem means a set of yes instances. Now we agree that a problem is a set of instances. How to represent instances? It turned out that we can use the most general data structure, strings. So, instance can be represented as a string over a particular alphabet, sigma. Instance can be encoded in character alphabet such as our ASCII code alphabet, or it can be encoded in the binary alphabet 0 and 1, or it can be encoded in the decimal alphabet 0 to 9. You may think that string is a one-dimensional data structure. It cannot be used to encode complex data structure, such as a binary tree. However, with proper use of parentheses, you can encode any complex data structure. For example, this binary tree, rooted and 23, left sub 3, and right sub 3, can be encoded in this format. The root and in parentheses for the left sub 3, and in parentheses the encoding for the right sub 3. So using this encoding scheme, this binary tree can be encoded as root 23, left sub 3, right sub 3. And the left sub 3 is rooted at 45, left sub 3, 3, and right sub 3, 18, and so on and so forth. Let us summarize what we got so far. We agree that problem means decision problem. And we also agree that problem means the set of instances corresponding to the yes answer. In other words, problem means the set of yes instances. And the instance can be encoded using string. Therefore, a decision problem is a set of string. Well, a set of string over a particular alphabet is called a language over the alphabet. Therefore, we can conclude that problem means language. Problem are simply language. Language means problem. Problem means language. So, a problem means a set of string corresponding to the yes instances. Then, how to solve the problem? What do we mean by solving a problem? We solve a problem by designing a machine or automaton. And this machine will process the character in a string and to decide whether the string is a yes instance or a no instance. If it belongs to the yes instance, you say the machine accept the string. Otherwise, we say that the machine reject the string. Over the past 60-70 years, we have developed different type of machines. For example, we will discuss finite state automata, push down automata, and Turing machines. Turing machine will be the ultimate version of machines. In other words, anything that can be computed by Turing machine. So to some extent, Turing machines answer what to mean by computation. We shall concentrate on the simplest machine, finite state automata, in this lesson. This is a diagrammatic represent of a simple finite automaton. This machine has two states, even and odd. The even state is highlighted with a triangle, meaning it is the initial state. If we reset the machine is in this particular initial state. This state odd, which is double frame, is called a final state. If a machine after process all the character in the input string and the machine go into final state, we say that the machine accept the input. Otherwise, we say that the machine reject the input. Other than the state, machine has transition represented by the edge. So for example, in the state even, when see a 0, it will stay at the even state. However, in the even state, we see a 1, the machine will jump to the odd state. Similarly, in the odd state, machine will stay in the odd state on 0, and it will jump to even state on input 1. Mathematically, a finite automaton is a construct with 5 components. Quintuple means 5 components. Q, sigma, delta, Qs, and F. Where Q is a set of states, it must be a finite set. So this gives this automaton the name finite state automaton. Sigma is the alphabet. So in this machine, the alphabet is 0 and 1. Delta is a transition function. So it maps from the current state and the input to the next state. Qs is the initial state. In this particular case, Qs is even. F is the set of final state. And in this case, odd is one of the final states. Note that there can be many final states, but only one initial state. In this slide, we look into some notation of the string data structure. So we assume sigma is a finite alphabet, consists of A1, A2, and AM. Assume that X and Y are two strings over this particular alphabet. From time to time, you will see this notation, sigma star. It represents the set of string over sigma. Bear in mind that sigma is finite. We got only finite number of characters. But sigma star is an infinite set. There are infinite number of string over sigma. Among this string, one particular string is called empty string. Empty string means no character inside there. We normally use lambda or epsilon to represent the empty string. Otherwise, you cannot see it because empty string don't have any character. So we use these two special characters to represent empty string. The most important operator for string is the concatenation operator. We use dot to denote the concatenation operator. So x dot y means the longer string consists of all the character x followed by all the character in y. Once we got the concatenation operator, we can define the power operator. X raised to the power n means x concat itself n time. So x to the power 3 means x concat x concat x. We assume that we got one function count, which can count the number of substring x in the input string s. Okay, so I give you a long string s and I give you a shorter string x, and this function will return the number of occurrence of x inside s. Let's look at a very simple computational problem called odd parity problem. Odd parity problem means what? Input is a binary string. In other words, s belongs to sigma star and sigma is 0, 1. The output is yes if s contains odd number of 1. In other words, it will count the number of 1 in s, and you perform modulus operator, modulus 2. That means the count divided by 2 take remainder, and if the remainder is 1, that means the count is an odd number. In this case, you expect the answer yes, otherwise you expect the answer no. For this problem, the corresponding language is L, specified as the set of string s belong to sigma star, sigma equal to 0, 1, and you will count the number of 1 in s, mod 2 equal to 1. In other words, odd number of 1. So example of string in L are 1. You got only 1, 1. 0, 0, 1, 0, also 1, 1. 0, 1, 0, 0, 1, 1, 0, 3, 1. All this got odd number 1, and we expect answer yes. It turned out that this simple machine solved the odd parity problem perfectly. The idea is the even state indicate that the machine has scanned even number of 1 so far, and similarly odd mean the machine has scanned odd number 1. So now the machine has assume the machine has scanned even number 1. When see the next input 1, the machine will move to odd, saying that it has seen odd number 1. Similarly, at the odd state, which indicate that so far it has seen odd number 1, it will see another 1, then become even, and if you see a 0, it will stay in the same state because 0 doesn't increment the count, doesn't affect the count. The state transition can be represented as a table. This table actually gives the definition of the state transition function, delta. So in the even state, when you see a character 0, it goes to even state. So this is the represent as this H.
In the even state, you see a 1, you go to odd state. That means even, see a 1, go to odd state, and so on and so forth. Let's look at how a machine processes the input. So we assume that input is as consists of 0, 1, 1, 0. An even number of 1 in the input, so the machine should reject the input. Imagine we start the machine. The machine should stay in the initial configuration. Consists of the initial state even, and all the input are placed in the input reader. So at this initial configuration, the machine in the state even read the character 0, it will stay in the even state. And the 0 has been processed, so disappear already. So the next input will be 1. And even state, you see a 1, it will go into the odd state. So the 1 has been processed, so disappear. So the remaining input is 1, 0. At the odd state, you see the 1, it go into even state. And the remaining input is 0. And finally, the machine stay in the even state after process the last character 0. And the input is empty. And the machine stop. No more input. The machine cannot move anymore. And you observe the state of the machine is not in the final state. So we say that the machine reject the input. Let's look at another test case. This time, the input S consists of 0, 1, 1, 0, 1, which has 3, 1, odd number of 1s. So the machine should accept the input. Again, the machine is at the initial configuration at the very beginning. So even and all the input 0, 1, 1, 0, 1. And the execution is represented this way: from the initial configuration, go to next configuration, go to next configuration, go to next configuration, next configuration, and finally the final configuration is odd lambda. So the machine, after process all the character, it go into odd state, which is the final state. And in this case, we say that the machine accepts the input. This is summarize the execution of a final state automaton. When we start the machine is in the initial configuration. Consists of the initial state, and all the input are placed in the input reader. So the machine, from the initial configuration, it will go to next configuration and so on and so forth. And finally, machine stop. How the machine move from one configuration to the next configuration? Assuming that the current configuration is Q1 and the first character in the input is A, the remaining character is X. In other words, all the character inside the input reader is A concat X. A is a single character and X is a string. We assume that the transition function bring Q1 to Q2 when the next input is A. So in the state Q1, it will read the character A go to Q2. So in this case, in the state Q1, it read the character A, it will go into Q2. And Q2 considered processed already, so it's removed from the input, and the input left only the string X. And in this way, X will inside the input reader will getting shorter and shorter and eventually become an empty string. And at that time, the machine stopped. So finite state automata are the simplest machines. The machine can only solve simple problem, and we call that kind of problem regular problem. In terms of languages, the set of language accepted by the regular automata are called regular languages. Okay, formally, assuming S is a string, we say that the machine accepts the string S if and only if there is a sequence of move. Move means change of configuration that bring the machine from the initial configuration. Initial configuration means what? The state is the initial state and all the character in the input are placed in the input reader to a final configuration. Final configuration means no more input and the state is a final state. That means that Q belongs to F, the set of all possible final states. All the string accepted by the machine form a language, and this language can be denoted as language of the machine, L of M. So L is a regular language if and only if it can be processed, it can be recognized by a finite state automata. In other words, if L is equal to L of a finite state machine M, then we say that L is a regular language. Exercise: what is the language recognized by this finite automaton? This finite state automaton consists of 5 states. Initial state Q0 and Q0 also the final state. This machine, the transition function look complicated. It is important to try to understand the role of each state. In order to do so, try to run some test input and observe where the machine go to. For example, after process 100, 100, it go to Q4. After process 101, it stay into 101, it's going to Q0. After process 110, 110, it go to Q1. Process 1111, 1111, it go to Q0. And you build a table and try to observe the input and the state it go to. So the state will be able to classify the input into different categories. For example, let's try to summarize. After process 000, it will go into Q0. After process 001, it go to Q1. 010, it go to Q2. 011 go to Q3. 100 go to Q4. 101 go to Q0. 110 go to Q1. 111 go to Q2. If you observe the input string as a binary number, amazingly you will see that the state after it processed the input corresponding to the binary value mod 5. You can see that this is a binary 0, it go to 0, binary 1 go to 1, Binary 3 go to 3. Binary 4 go to 4. Binary 5 go to 0. Binary 6 go to 1, because 6 mod 5 is 1. 7 mod 5 is 2. So actually this machine, actually every state represent the binary input, recognize binary input mod 5. So Q2 mean it had encountered a binary input, and so far the value of the binary input mod 5 is 2. So in this state you see one more 1. So for example, my state is 1 0. If you see a 1, that means what? Essentially is 1 0 times 2. That means 2 times 2 plus 1. When you see a 1, that means the binary value become what? 2 times the current value plus 1. So 2 times 2 plus 1 is 5. So you go to Q0. On the other hand, if you see a 0, that means left shift. Left shift means times 2. So Q2 times 2 become 4. Q4 see a 0 means times 2. Q4 times 2, 4 times 2 is 8. 8 mod 5 is 3. Q4 see a 1, that means what? Q4, 4 times 2 plus 1. 4 times 2 is 8 plus 1 is 9. 9 mod 5 is 4. So basically it's based on this thing. The binary value of x dot 0 is a binary value of x times 2. The binary value of x dot 1 is the binary value of x dot 0 times 2 plus 1. Actually, this machine is built based on this formula. And since Q0 is the final state, so this machine recognize binary input where the binary value mod 5 is 0. This is the end of part 1 of lesson 3. Thank you for your participation.